So this is video 8 in the series of videos on ship stability, and today's topic is transverse statical stability. So in this transverse statical stability, I'll discuss a bit of theory and then end this video with 3 or 4 different types of questions to show you how the theory falls in line with the numericals that you may get in the exams. Alright, so let's start with taking an example of an upright vessel. Now this is a box-shaped upright vessel, and let's say that when a ship is floating in a still water and that means she's not rolling or pitching, her center of gravity and her center of buoyancy will be in vertical lines. So COG stands for center of gravity and COB is center of buoyancy, and the center of gravity, the force of gravity, acts downwards and the force of buoyancy acts upwards. Alright, so and these forces of gravity and buoyancy, being equal and opposite, cancel each other out, and the ship attains a state of what we call static equilibrium. So in this state, the ship is upright, there is no forces listing or heeling it, the force of gravity and buoyancy are equal and opposite, and they cancel each other out. Alright, however, when a vessel is heeled or listed, what happens then? So to know the difference between heeling and listing, heel is the transverse inclination of the ship, which is caused by the external forces such as waves, wind, over-tight moorings, centrifugal force during course alterations, etc. So it is caused more by natural conditions and conditions other than cargo. Alright. So since there is no transverse shift of any cargo or weights on board, the position of the center of the gravity of the ship remains unaffected in heeling. Alright, so this is only the case of heeling. So in heeling, the center of gravity doesn't shift its position. So what is list? List is the transverse inclination caused by unequal distribution of weights on either side of the center line of the ship. So list involves distribution of weights, cargo. Alright, it has nothing to do with natural phenomena like winds and waves or conditions like moorings. Due to the shift in the weights, the list is caused when the center of the gravity of the ship is not on the center line. Alright, so as soon as you shift weight, you load, discharge, unequal distribution of weights takes place. The center of the gravity of the ship shifts, because of which the vessel lists. A ship with a list becomes upright only if the center of gravity is brought back to the center line. Alright, so in today's video we'll be focusing more on heeling, not on listing, but I thought we'll discuss list as well, just to show you the difference between heeling and listing. Listing we'll discuss in a future videos, so I'll be coming out with a video very soon, and you will see what is the effect of list on a ship's center of gravity and how we can correct that. We'll be using different numericals and examples to show you that. Today's video is only about heeling. Heeling caused by winds, waves, over-tight moorings, or due to centrifugal force when the ship is involved in heavy course alteration. Then of course the force of buoyancy shifts, because of which the ship also sometimes heels over on one side. So that's the topic today. So we'll focus on when the ship is heeled over to one side. So in this case, the ship is heeled onto the starboard side. Her underwater volume increases on the starboard side, as you can see. Right? So if this is starboard side, this is starboard side, and this is port side. So the right side is starboard side. When the ship is listing, and I'll show you what is so this is the water level. Alright, so the black line is the water level here. This is the water level. Right? So the ship is now, the starboard side of the ship is under the water. When the ship is under the water, you can see that her underwater volume on the starboard side is increasing. So underwater volume refers to the volume of the ship which is under the water, and of course it decreases, the underwater volume decreases on the port side, because the ship's port side is now coming out of the water. Right? So the center of the buoyancy, which is the geometric center of the underwater volume of the ship, shifts to the lower side, which is the starboard side in this case. And that is why you can see there is a shift in the center of the buoyancy from B to B1. In the diagram above, the small b becomes a geometric center of the emerged part of out of the water. That is the wedge, the immersed part of the wedge out of the water. Alright, that is B. So that is the immersed part is, let me show you by a green color. Right, this is the immersed part. So this geometric center of the immersed part or the immersed wedge is B, small b. Similarly, small b1 becomes the geometric center of the immersed part of the wedge inside the water. And again, let me show you with a green color. I wish we had more colors here. This is the geometric center of b1. Alright, then capital B becomes the center of buoyancy before the vessel was heeling, as shown above in the drawing, and capital B1 becomes the center of buoyancy of the ship after heeling, as you can see here. Alright, because the center of buoyancy is shifting. Because there is no shifting of weights here, the center of gravity remains where it is, only the center of buoyancy shifts. BB1 is the shift of the center of buoyancy caused by heeling. So few things you have to remember is here, BB1 or small b1 is parallel to capital B and capital B1. Capital B, capital B1 is not parallel to the waterline and not even parallel to the keel. If you see the diagram above, capital B and capital B1 are not parallel to the waterline and they are not parallel to the keel as well. Alright, it may seem so in the drawing here, but it's not the case. An angle G, B and B1, where B is our capital, is not a right angle. So this angle here, this is not a right angle. So I will erase this. This angle, you think it's a right angle, it's not a right angle. Alright, it's a normal angle. Alright, so these are some of the things you have to remember. Now what happens when the center of the buoyancy shifts to the new immersed underwater volume? So you can see the diagram here that when the center of buoyancy shifts, the center of the buoyancy then acts upwards through a new position and it cuts the vessel's center line at a new position called the M. This new position is called transverse metacentre. So on heeling, the new center of buoyancy acting vertically upwards cuts the center line of the ship at M. Height above the keel is referred to as Km. So height above the height of M above the keel is referred to as Km, which is also called transverse metacentre, metacentric height rather. And this height increases as the angle of heel increases until it reaches a maximum value at some large angle of heel, after which it starts to decrease as the angle of heel increases. However, over small angles of heel up to about 15 degrees, the increase of Km or metacentric height is generally very small. Hence, for small angles of heel, the metacentric height is considered constant and referred to as initial Km for stability calculations. Hence, Km becomes Kb plus Bm. I was referring to it as metacentric height, which is not really right. Metacentric height would be Gm. So call it transverse metacentre only. Alright, so height of the transverse metacentre from the keel. My apologies for the error. Alright, so in this case, Km becomes Kb plus Bm. Alright, now if we move on, metacentric height. Metacentric height is actually the distance between center of gravity and the transverse metacentre, which is GM. That would be the correct definition. Alright, so GM is the distance between the center of the gravity of the ship and the transverse metacentre. So GM is positive when G is below M, and GM is negative when G is above M. Vessels should be sailing out with a positive GM. Some ships have a small GM, some ships have big GM, but GM should be positive for your vessel to be sailing out before your vessel sails out. Alright, now some ships have naturally low GM, that's fine, but it should still be positive. Over small angles of heel, GM is also considered constant, just like Km, and referred to as initial GM. Alright, just like Km is referred to as initial Km, Gm is also referred to as initial Gm. Let me change the color of the pen, otherwise it's all becoming very similar. So I'll start with the green pen now. Then you have a concept of writing lever, which is GZ. What is writing lever? So let me show this in the diagram above. So you can see here, this is writing lever GZ. Alright, this lever is called writing lever. So what is writing lever? When a vessel is heeled, the force of the buoyancy acting vertically upwards through the new position of center of buoyancy becomes separated from the force of gravity acting vertically downwards through the center of gravity by a horizontal distance called the writing lever. The writing lever or GZ increases as the angle of heel increases until it reaches a maximum value at some large angle of heel. Thereafter, GZ decreases as angle of heel increases. This is very similar to the concept of Km. For small angles of heel up to 15 degrees, wherein Km and hence Gm may be considered constant, GZ is given by this formula here. GZ equals Gm sine theta, where theta is the angle of heel and Gm is the initial Gm. For large angles of heel, GZ equals sine theta multiplied by, in brackets, Gm, which is the initial Gm, plus half of Bm tan squared theta, where theta is of course the angle of heel. Bm is the height of the initial metacentre above the COB before heeling. This formula can be used whenever the ship's sides within the immersed wedge and the emerged wedge are parallel, that is until the deck edge goes under the water. So if I go back to the diagram above, you can see that this line here is the GZ. This becomes a writing lever. Alright, so when the center of the buoyancy shifts to the new underwater volume of the immersed, the new underwater volume cuts the ship's center line at a new position, which is called the transverse metacentre. But due to this, it becomes separated from the center of gravity by a horizontal distance, as you can see is GZ, and that's called the writing lever. Now this writing lever forms a couple or a moment which tends to return the vessel to the upright position. The moment of this couple is a measure of the tendency of the vessel to return to upright and hence called the writing moment or RM. Writing moment or RM equals displacement multiplied by GZ, that is writing lever for small angles of heel, say up to about 15 degrees. But GZ equals Gm sine theta, as you have seen above. GZ equals Gm sine theta here, right? Therefore, writing moment will become W into Gm sine theta. So displacement by GZ, but GZ equals Gm sine theta. Therefore, writing moment can also be written as displacement multiplied by Gm sine theta, where theta is the angle of heel. Alright, so we have discussed some of the theory here above. Let us put this in the context of the numericals and the questions that you may get in the exam. So the first question says, there is a ship of 10,000 tons displacement. It has a GM of 0.4 meters. You have to calculate the moment of statical stability when the vessel is heeled by 5 degrees. So you have got the angle of heel, you have got the GM, and you have got the displacement. You have simply need to calculate the moment of statical stability. Now if I didn't say this already, the writing moment is also called the moment of statical stability. So you simply have to put in the values for the writing moment. So the writing moment will be equal to displacement multiplied by Gm sine theta, as you have seen above in the formula. Displacement is given to you, Gm is given to you, and theta is given to you as the angle of heel. Your writing moment becomes 348.62 tons meter. Alright, this weight will bring the vessel back to the upright position. The second question says that a ship of 12,000 tons displacement is heeled by 6 degrees. Her writing lever, not writing moment, but her writing lever, which is GZ, is then 0.1 meter. Find the moment of statical stability, which is her writing moment, if her Km is 8.2 meters also find her kg. Alright, kg is the distance of the keel from to the center of the gravity. So what's the solution? So for small angles of heel up to about 15 degrees, and in this case the heel is 6 degrees, gz, which is the righting lever, equals to gm sine theta, as we have seen above. Gz is given to you as 0.1, gm is not given to you, and then sine 6 degrees. 6 degrees is the angle of heel. Take your knowns to one side, keep your unknown to the other. Gm then becomes 0.1 divided by sine 6, which is equal to 0.96. Alright, I have just stuck to 2 decimal places. Gm is normally written in 2 decimal places. Once you get your Gm, you have to calculate your righting moment. Righting moment equals displacement multiplied by Gm multiplied by sine theta. So your displacement is 12,000, Gm is 0.96 from here, and sine of 6 degrees, which gives you your righting moment of 1204 tons meter. Finally, your Km is given to you. You have to calculate your kg. So Km minus Gm equals kg. Km is 8.2 meters, Gm is 0.96 meters. Your kg will be Km minus Gm, which is equal to kg equals 7.24 meters. Finally, the last question is that there is a ship of 8,000 tons displacement which has a kb of 3.5 meters, km of 6.5 meters, and kg of 6 meters. You have to find the moment of statical stability, or the righting moment, at 20 degrees of heel, which is not a small angle of heel now. This is a big angle of heel. It's more than 15 degrees. But you have to assume that she is still wall-sided at that angle of heel. Alright, so remember, we talked about this before, but today I'll show it to you in the example. So if you are saying she's wall-sided at that angle of heel, so the sides are wall-shaped, you can use this formula here for righting lever. So anyhow, let's use the information which is given to us first. We have Km given to us and Kg given to us, so we can find out Gm. So Km minus Kg equals Gm. We need Gm for the formula. So Km is 6.5 minus 6 meters will give us a Gm of 0.5 meters. Similarly, Km is given to us and Kb is given to us. Km minus Kb is equal to Bm. So 6.5 minus 3.5 is equal to Bm. So our Bm is 3 meters. So I've always told you before that whenever you have to find something out in stability questions or any other question, you just have to see what is given to you and what needs to be found out. If you know the formula, then all you have to do is basically start ticking off what you have in the formula and what you don't have. When you find out what you don't have, just use the information available to you to find out what you don't have. I'm sure you will be able to find out all the required missing parts. Alright, so of course, when the question says we have to find our righting moment, or rather our moment of statical stability, before we do that, we need to know what is our righting lever. Find out our righting lever for wall-sided vessel. After angle of heeling, we can use this formula for large angles of heel. So we simply put in the values of sine theta, then we put in the value of Gm, half of Bm into tan square of theta again. Check your values with the values given or written by me. You should be getting a righting lever of 0.239 meters. Now remember, righting lever is in meters, righting moment is in tons meter. Once you get your Gz, all you have to do is basically put in the formula of righting moment, which is displacement by Gz, or 8,000 tons multiplied by Gz of 0.239 meters, and you will get righting moment of 1912 tons per meter. So these are different questions that I took. Again, I repeat myself that whenever you read a question in ship stability, write down first what you have to find out, and then you can work your way backwards as well. So in this question, you had to find out the moment of statical stability, which is your righting moment. You could have started the question at this level here. At this level, you would have the displacement, but your Gz would have been missing. So you write down the formula for Gz over here. When you write down the formula for the Gz, use the right formula, because this is a wall-sided vessel after an angle of heeling, as also it's for a large angle of heel greater than 15 degrees. Once you write down the formula, start taking off what is given to you in the question. So in this case, the question gave you theta, but it didn't give you Gm. It didn't give you Bm and give you theta again. Because your Gm and Bm would have been missing, you would work your way backwards and you would find out GM and BM from the information given to you. In this case, KM, KG and BM was given to you. Sorry, KM, KG and KB was given to you. So you could find out GM and BM. That's the formula, or that's the technique of solving any numerical based questions. If you know the formula to what you have to find out, simply start taking off what you have and start finding out what you don't have from the information given to you in the question. Alright, so I hope this video was useful to you. If you have any questions, please write to me in the comment section, and I'm happy to address them and answer them over the comment section as well. I'll see you soon with my next video. That would be video 9 in the series of ship stability. For all the previous videos, I'll give you a link to those videos as well. I'll recommend you guys watching it in series, because there are many terms here that I discussed and which I didn't explain, because I assume that you are familiar with those terms. To become familiar with those terms, watch the stability series in series starting from video 1, and I'll give you the links to those videos in the description section below. Thank you for watching and thank you for subscribing. I'll see you soon with my